Now I will present you the super vector machine. So SVM, as we call them, are a family, or I would say some model for classification, basically, but also used for regression. But we will see the classification models here, where we aim at maximizing the geometric margins. So the point is that with this model, we aim at finding the optimal position for the separating hyperplane to use over a given data set. It is argued, in fact, that such criterion of maximizing the margin is in fact the right criterion. According to the version space, we have some theory that is supporting this quite well, that it is the right thing to do in terms of, at least a right thing to do in terms of classification, learning a classifier. And as such, the model is developed for a linear discriminant, and this is the one we will see next. I would say this is the best among what we saw so far with perceptron, with least square regression, with also what we saw last week, logistic regression are okay. We are going from better to better, but here I would say the SVM is really a good model for training a linear discriminant. And we are even able to extend this model from linear discriminant to nonlinear cases through the use of a kernel function. So with a kernel function, we are able to map this problem into a nonlinear problem, but where we will use a machine we develop for linear discriminants to solve it. So talking about version space, which is kind of giving the intuition of doing geometric margin maximization. If we are looking at this case, we have, in fact, a data set of two classes. We have the red circles, the blue squares, and we can use some kind of box classifier. Basically, it's kind of surrounding box where we can change the size and the position, but the point is that inside the box, it's one class. Outside the box, it's another class. We can see here different versions of the classifier, different possibilities. And I would say these three possibilities, if you look at the three boxes, we have like the biggest one, which is called J. We have the smallest one, which is called S. And we have one in the middle, which is not called anything, but we can see it corresponds to the light gray box plus, but it covers the light gray space plus the white space. So we have three versions here. And these three versions are fine according to the training data set accuracy. You know, we have 100% accuracy here. There are no samples from the training set that are misclassified according to what we have here. And as such, we have like what we call G is the most general hypothesis. So this is the hypothesis that is the most general, that is the biggest one. And if you see it, in fact, it is expanded to be really close to some blue samples here. So it is kind of on the four sides of the box is really on some blue square samples. So it is the most general one. We cannot go on with a bigger box. Likewise, we have S, which is the smallest possible box, which are really close to four samples, which are really on the four borders or the four sides of the box here. So we cannot be smaller than this while keeping an accuracy of 100%. And in between, we have different possibilities. And all these are correct in terms of accuracy, but in terms of generalization, eventually, can we generalize on that? Well, it seems that something in between, something that would try to keep some safe zone from the decision frontier to the sample is likely to be the best option, because we can get more samples that will be maybe slightly around but closer to the frontiers that what we have now as training set, and these can be misclassified if the frontiers are too close to the training samples, while being in between, being really halfway, maximizing the distance, the margin to the current sample is likely to get us in a position where we will not get that much samples in a test time that will be on the wrong side. assuming that the test samples are following the same distribution than the trained samples. So going back to our SVM model, we are looking to maximize the geometric margins. So we are looking to figure out, find the weights W and W0 that are maximizing the geometric margin for our data set, big X here, with labels given as either -1 or +1. So we are still in a linear discriminant case with two classes. And we are looking at finding out the configuration of the parameters of H, where H aims at giving us either a negative or positive value, and R is giving us the right sign for each sample, either one class or the other class according to the value of R. So one thing we want to compute, we need to get is the distance to the data separating hyperplane. You know, we are looking at the distance from a sample to the separating hyperplane given by W0, and that distance is given, as we saw just before, just the presentation before, according to the geometry of linear discriminant, is given with this. You know, we have the absolute value of H here, which is basically W transpose XT plus W0, absolute value, divided by the norm of W. And this is important to get things normalized, and this is giving us the distance from the point to the plane. And if we look at this, in fact, to get the absolute value, knowing that we have a model that is correctly classifying our data, the sign of H and the sign of R should be the same. So here, if we have a positive R equal to +1, H should be positive also. So +1 times positive H, keep it positive. But here, I would say the nice thing is that by using this for a negative R, if we expect the H to also be negative, so something negative times -1 is positive. So that's a way to emulate here somehow the absolute value true. So we are emulating the absolute value here by multiplying by RT. And as such, we want this distance to be greater than some kind of threshold, which is called rho here, which is corresponding to our margin. So we want all samples to be outside that margin. We want them to be with a value of RT multiplied by HX, which is developed here as W transpose XT plus W0, all this divided by the norm of W. We want all this to be greater than rho, because this is the distance from the sample to the separating hyperplane, and we want all samples to be at least at a distance rho from that frontier. And this is the margin. This is what we want to be maximal. We want to maximize that margin rho. So getting back at that stuff, you know, just remember that in fact, absolute value of HX divided by the norm of W is corresponding to the minimum distance from X to the hyperplane. So one other thing we need to take into account is the fact that W transpose XT plus W0 is underdetermined. You know, there are more variables than there are equations, so there is an infinity of solutions. We can get different settings that are corresponding exactly to that. So basically here, if we have this thing, so a vector of 2.5 with a constant W0 of 1, if we multiply everything by 0.5, so dividing by 2, we got this configuration, which is all numbers divided by 2. This is totally equivalent in terms of the discriminating hyperplane, the placement of the hyperplane in space, to the first one. And likewise, if we multiply by 10 the first configuration, we've got this 25 and 10 as values for W0, and this corresponds to the exact same hyperplane that what we have first. So we have three configurations that are equivalent. So now, just to constrain that, we can set that rho, which is the margin times the norm of W, should be equal to 0. So we'd set that constraint, and that will kind of will add an extra equation to satisfy that will get us into something that where what we see here as a system that is underdetermined is no more the case anymore. So, and that allows us to simplify things in the sense that if we take the equation that we have at last slide, we can convert this to something like that. We can say basically that W transpose xt plus W0 is greater than 0.1 for RT of +1. And conversely, the same value is less than -1 for samples from the other class. So an equivalent formulation, if we go back with the RT here, is simply to say that RT times W transpose xt plus W0 is greater than 1 or equal when we are already on the frontier, on the margin. And here to maximize that margin, because we state that thing here, so we know that we state that rho, the norm of W is equal to 1. So basically we know that rho is equal to 1 given the constraint that we put here. So by minimizing the norm of W, we are maximizing the margin rho. And this is a good thing. This is what we want to achieve. So if we are looking back at our model, now we are adding some samples. We see, in fact, again, an example of some samples in two classes. So we have the blue squares here. We have the red circles there. And we assign, in fact, the red circles to the class of C2 negatives, and we assign the blue squares to the class C1 as the positive value for H. We can see here that we have 3 samples that are really on the margin. We have that one that is defined at H equal to -1, and we have these 2 ones which are defined as Hxt equal to +1. The others have an H, corresponding H that is either bigger than 1 or less than -1. And what we see here is that all this zone, in between the 2 dashed lines, is a kind of no man's land zone, a zone where we have no samples, and this is our margin. And so we want to maximize that distance. We want to maximize the distance between the hyperplane, just said otherwise, we want to maximize between the hyperplane and the closest sample, which distance is 1 over norm of W, basically rho. And this distance is the same on both sides. We have this distance for that sample, but we also have the same distance for the other sample, also at 1 over norm of W, which is rho, basically here. And so this is what we want. And as such, we want to get a placement of that hyperplane that will maximize the margins.